Okay. So I first tried this failed miserably. Uh, right. And now I know what went wrong. So let's do it the correct way now. So first of all, let me explain what actually a manometer does. It measures the static pressure for your pipe. So if you have a pipe like this, and then um, you have something like this. Okay, so you have this thing, but okay, maybe just put this open to atmosphere. Who knows? Maybe that will be better. So then it will just measure the gauge pressure or whatever, or maybe just put a just put a vacuum in there, and then it's gonna measure the actual pressure, whatever. So this is kind of like a test tube or whatever this thing is. It just contains some fluid. Sometimes they take mercury. In this case, I'm just taking water. So this is water, as well as this thing is also water. Now, we are going to assume a few things. First assumption is that throughout this fluid, there's no viscosity. So there's no viscous force, basically. We know water has viscosity, but then assume there's no viscous forces, right? So basically the viscosity is zero. You can assume that. Okay. Now, the initial flow was completely laminar, and the u vectors throughout this cross section, they were the same vectors. So that just means that there was zero curl, which means no vorticity initially. So using Kelvin's vorticity theorem, what we can say is that there will be no vorticity throughout any streamline. So throughout this fluid, there's no vorticity, which means that you can apply the Bernoulli's equation between any 2 points. Okay, so you can take this point and apply the equation. Yeah, you will get something, right? At this point, the pressure is zero. Let's say the height of this thing is just h. So we'll have just rho gh and okay, rho gh plus. So assume there's some flow velocity. So let's just say in this direction, because it should be perpendicular to the surface, right? It can't have any component in this direction or in this direction. That would mean that the surface itself is moving, which doesn't make any sense. So the only way this could happen throughout the boundary, right? So everywhere on the boundary, you have the flow velocity, or near the boundary, you have the flow velocity in the tangential directions. Let's just say this velocity is v. Over here, it's u, of course. So then you just have this thing plus half rho v squared. That is equal to, so over here, the pressure is, let's just say P. Then you have half rho U squared. All right. That looks cool, doesn't it? Now, what we observe is that rho GH is in fact equal to the pressure. Basically, like these two terms get cancelled. And yeah, that just means V equal to U. So because V equal to U, you have the rho GH thing being equal to the pressure. So you might think, okay, why is this happening? Why is V equal to U? And first of all, why is this even moving? Shouldn't this bulk be in fact stationary? Well, no, it's not. You see that as water starts to, okay, so you are going along this streamline. So these streamlines proceed, and now what will happen? Now you encounter this thing. Of course, the streamlines have to go somewhere. They can't just go straight. There's a problem with that, because if they just go straight, then the water over here, it's not moving, but over here it's moving. So there must be viscous forces, right? And yeah, that would just mean that our assumption fails that we can apply the Bernoulli's equation, right? And also, this is not what actually happens. So there are no viscous forces, because we already assumed that there should not be any viscous forces. So what exactly is happening? The streams are going inside. Yeah, that's what's happening. What's happening is that the streams are going inside, and something like this is happening. Yeah. So remember, we already assumed that viscosity is zero, which means that the water molecules, they are not, and also they are not They are not interacting with these surfaces in any way. Okay, so there is really just no way of introducing vorticity, which means your Bernoulli equation is still correct, right? We can apply it on any streamline. And also, because all these streamlines start from this cross section, and then throughout this cross section we have the same constant. The Bernoulli's equation has the same constant for each streamline. So what we can do is um, apply the equation at any 2 points, yeah, throughout the fluid, assuming that the fluid is in steady state and everything. Yeah, you know the usual assumptions. So what's happening is that the fluid is actually going inside, and then it's doing something like this. And then, yeah, you know the thing. So this is what's happening. And then right at this place, you of course have velocity v. So what really should be happening is that you actually destroy it in a better way. So this is this opening over here. Okay, this is our, let's just say this is slightly rounded, just so that I can draw it easily. Now you have fluid flowing in, and it never actually leaves the surface when it's close to surface, and just goes like that. So that's one streamline. Then you have a streamline, I mean the same streamline, in fact this thing. I'm not going to draw the upper portion, it's just coming and then going like this. Okay, you also have streamlines over here. So there's some distance from this thing, and then you have streamlines over here which are just going like this. And in between that, there are streamlines going in various different directions, and then coming from all these different directions back into this point and then going. Now you might say, okay, why is this? Why should I believe you? Right? Consider what would happen if you started to decrease the height of this thing. If you start to decrease the height, at some point, this will just become flat, right? So when it reaches over here, it just becomes like you have this thing. So you just actually draw the thing. Maybe not the best way to be doing it. Yeah, definitely not the best way, because we use this kind of setup so that we can actually get the height, right? Yeah. Okay, what should I then tell you so that I can satisfy the thing? Okay, think about it. I wish there was just something that could measure pressure directly without having to do all of this height stuff. That would be much better, right? Sure, that definitely would be much better. What I was thinking of is that you could just, figure out what is the pressure at this point, right? Yeah, or let's just say at this point or whatever. In fact, the thing is, maybe we should not be thinking about it, like we should not let it have a height. Instead, just make it like this. So now this test tube or whatever you want to call it, it is not going to have the full height that it can have. Instead, it will just cut short. And now the pressure over there, what's that going to be, right? So if this was not moving, the water was not moving, what would the pressure be? It will just be this pressure minus rho g times whatever this height is, right? And what I want to say is that even if it is moving, it will still be the same pressure. So that's because over here you have u, and over here as well you have u, right? That's what I want to prove. So how is this going to happen? Like, how can I prove that this will be the thing? I can't really prove it, but then I can give you a bit of, let's just say, you know, maybe I can suggest to you that this could be the case, right? So what I'm thinking of is that you make this test tube shorter and shorter and shorter, and then after some point, this actually becomes like just flat, and then this becomes this surface area, right? So this area becomes this area. In that case, you can agree that, so we can agree that the flow velocity is u, right next to the surface area. You can do that for sure. But what that means is that is that our yeah, like this flow is just U, and then this is also U, which means our pressure is really just um, P minus rho GH, right? Yeah, but H is of course this height. Now I know you might be saying, well, that's not really height, it's just the radius of the tube, and then it will be really short and whatever. But so this is what happens for water or some fluid like this, right? Now let me give you a better example where I can do this thing. So let's think about this. So you have this pipe in which air is flowing, and then you connect to it a glass tube just like we did previously, right? This contains whatever you want this to contain, maybe like mercury or whatever. So it contains mercury, and then on this end, this is open to the atmosphere. So this also contains mercury, right? Yeah. And then of course you can do the usual thing, like the difference in the height is going to give us the difference in the pressure, just multiplying by rho and G with the pressure, right? Yeah. Right. Now, when you will do, you will try to find out what this pressure is um, using hydrostats. I mean, this if this was not actually moving, then this pressure would be the same thing as this pressure, right? Because density is very small. So what I'm suggesting is that even when it is moving, this pressure is the same as that pressure because the flow velocity at this point is the same as over here, right? So the air is actually going like this. I know I can't really draw it well just in this, but still I'll try to draw it, and then maybe like that. Okay, you get the idea, right? That our velocity vector at this point will be u vector, right? So the pressure, or I should say the hydrostatic pressure, is still the same thing as what it was over here, which means that I mean, okay, these are just moving in this direction, right? All the molecules in bulk are moving in that direction, which means that the pressure that this surface receives is just because of the thermal motion. Or, okay, yeah, thermal motion, because now we are dealing with a gas and not a liquid anymore. So I can say that. So it's just the thermal motion that we are dealing with, and that's the pressure that it will feel, which is the same as the static pressure, right? It is the definition of the static pressure. Anyway, now that we know that, um, let me show you why I thought about this thing. So if suppose you extended this and then increased the volume of mercury so that it comes all the way till here, all right? Maybe I should draw it in a different way, whatever. So this tube is supposed to be in front of this pipe, so it's not a part of the pipe, all right? Just draw this to make it clear. So this is atmosphere coming in, right? And then this is the surface. This surface is of mercury. This is also surface of mercury. Okay. And okay, you know what? Just show that it's actually like this thing. Okay, maybe not like this, maybe like this thing. Okay, whatever. So now you can agree with me that the flow velocity is really just u vector over here, right? Yeah, because it's as if this thing, this surface was a part of the complete pipe, right? Even though it's not a part of the pipe, it's actually a different material surface. But still, you could assume that it's behaving very much the same way as the pipe's walls does, right? Because we already assumed that the gas does not interact with the surfaces like this surface or the walls of this pipe. It doesn't interact with that, right? Yeah, I mean, sure. So what that means is it really has u vector over it, right? The particles on this surface or over the surface have velocity u vector. And now you can surely say that the pressure felt by this will be the same thing as the static pressure, right? So if you start to decrease this from here, what do you think will happen? How would the pressure change? Would it change? Right? That's the kind of question. So I think it won't, because the flow velocity will still be u vector, and that's what we see experimentally, that the pressure does not change. Now I don't know if what I'm thinking is actually correct or not, that the flow velocity is u vector at that point, but I think it could be, right? What's stopping it from going inside the tube? If it can, it will. Yeah. And the other case, like you're talking about, which is that it does not go into the tube, that is more absurd, because if this, yeah, over here you have all the particles are just, stationary, and then here you have u vector. Then there's of course viscosity, right? So there will be, a random jumping of particles from here into there, and then from here into here, right? And because of that, this will be this will be slowed down, and this will start to move, right? So how is this steady state in that case? So that's why I think that this should be u vector over here as well. Like there's some distribution of u vectors, or okay, velocity vector in this region where air can come inside, right? And well, that also explains um, why you can still apply the Bernoulli's equation for the pitot tube, because in that case, so for a pitot tube, pitot tube, say something like this. In that case, along this cross section, the original u vector distribution was right. It was like symmetric, you could say so, right? So there is no reason for air to come inside and then do whatever it does over here, right? Because over here the air could leave. Once it comes inside, it can leave. Now if it comes inside, from where will it leave? Because there's a cylindrical symmetry. So how is this going to happen? From where will it leave? Right? That's a problematic thing. And you can still apply the Bernoulli's equation over here, right? So that's what we are going to do. We can still apply the Bernoulli's equation over here as well, right? Actually, we can apply it throughout. So it's supposed to be this, right? Something like that. So yeah, and then do the same thing as we did over here. Just add a mercury column so that you can measure the pressure. Okay, so maybe like this, I don't know. And you can, I think it's not too bad to assume that over here um, the air is not really moving, right? Is that so hard to assume? Because okay, even if it is moving, then it's like moving along the boundary, and then it has to go somewhere. Where will it go, right? So what I think feels correct is that throughout this region, u vector is just 0. Okay, and this region of u vector equal to 0 actually comes out of this tube and into this air, and then the streams are going away from this region. That makes sense. And okay, what about viscosity, you might ask? That isn't there viscosity involved in here as well? Well, yeah, there is. But what we can do is, just make this region so large, right? This region of u vector equal to 0, so large and thin, that the effects of viscosity can be neglected, right? Basically, yeah, you could do that, and I think it's gonna work. And also, okay, maybe it's not the correct way to be saying this, but then, well, whatever. So the force on our element dv, because of viscosity, that doesn't actually depend on partial v upon partial x, but partial squared vx upon partial squared of u vector upon partial x squared. So maybe the second derivatives are just 0. Who knows? So I think that was not a good thing to do, right? Even if your elements have 0 force because of viscosity, that does not mean that throughout it, like there's that it is 0, right? No, that what am I saying? Right. So the elements have 0 force because of viscosity. That could happen. No big deal with that. But that doesn't mean there's no viscosity, right? Yeah, like take the example of just a plate moving on water. The viscous forces on the sheets of water 0, right? But then there is viscous forces, right? There are viscous forces between this sheet and that sheet. It's just that the same and opposite viscous force is between this sheet and that sheet. So it cancels out and then you still get 0. But that does not mean there's no viscosity, right? Yeah. Yeah, that's a kind of a weird thing going on, isn't it? But then again, we assumed that it doesn't actually interact with the surface, right? So this still holds, I think, right? You can still apply Bernoulli's equation. I think it's not so hard to convince yourself that you can apply Bernoulli's equation in this case. Is it? I don't think so. Because we do apply Bernoulli's equation most of the time to get the formula, right? So yeah, I think that um, that is an okay justification for why the formulae are correct, right? So the last time the problem with my reasoning was that what I thought was that without viscosity you cannot have this thing working, right? Which is a very wrong thing. So I thought that the Bernoulli's equation is not applicable over there. There's viscosity, and then we don't need the Bernoulli's equation. Instead, we are just going to do the Eulerian equation and then get the pressure, right? At this point. Yeah, and in doing so, I assume there is viscosity so that this whole surface has u equal to 0 near it, which is wrong, right? I mean, first you assume there's no viscosity, and then now you assume there is viscosity. It doesn't make any sense, right? So now just assume there is no viscosity, and it still works out somehow, okay? And then over here as well, just assume there isn't any significant viscous forces, and then it still works out somehow, right? Seriously, I don't want to get into like the actual distribution of u vector in this space. No, I don't want to do that because first of all, I don't have the proper information for doing that. I don't know what assumptions to make. I mean, okay, like I started to do it. I thought, what can we do? Like, how would I try to do this thing? And then I suddenly realized that I don't know whether or not my fluid should be interacting with the surface or not, whether or not it should actually have viscous forces. And yeah, at that point, I realized that maybe it doesn't have to have viscous forces, and this still would work, right? And that's why I think this is a good justification. Anyway, now that that's done, just use the formula blindly without caring about the derivation, and let's get this thing done. Okay. Oops. And if someone from you knows a proper derivation for this thing, give me a link or give me a video or anything, right? And please don't like involve more concepts because I don't want to learn anything more than what is in this book and in my syllabus, because if I do that, I'll probably start learning even more, right? So it's kind of like a trap. Just start really small. You think, okay, it will just be 2 pages of derivation. How bad would it be, right? And then somehow to understand the 2 pages of derivation, you have to go through the whole Stack Exchange websites, and oh god, and it's just not good. Anyway, 317. Let's do it. A Python tube, okay, is mounted along the axis of a gas pipeline whose cross-section area is equal to S. Assuming the viscosity to be negligible, find the volume of the gas flowing across the section of pipe per unit time. If the difference in the liquid columns is equal to delta H and the density of liquids and the gas are rho naught and rho respectively. Okay, so the liquid has density rho naught and the gas has density rho. Wait, the gas has density? Why are we doing that? Oh, that's not good. The gas has density. Huh. Okay, whatever. Viscosity is negligible. Find the so viscosity once again viscosity is negligible. So yeah, you are already assuming that. Find the volume of the gas flowing across the section of the pipe per unit time. So just want Q, which is yeah, okay, fine. If the difference in the liquid columns is equal to delta H, What's the cross section of this tube though? Oh yeah, is equal to S. So basically all you have to figure out is just the flow velocity, right? Yeah. So let's do it. Let's do it. So we'll have 3 points where we'll apply the Bernoulli's equation. You will have this point, right? At the very start, then you will have this point, and you will have this point. So they are all connected by the same the air thing, right? And then we can actually do this thing. So they are telling us to use the density of gas, which is weird because usually that is very small compared to rho of the liquid, but still we'll use it anyway. So over here, um, which will call as our datum. So the height of this thing is 0, right? We are setting it as 0. What is the thing? So it's just the pressure, whatever it's gonna have. Pressure. So what am I writing? This is not supposed to be. What is it? Okay, P plus, well, 0 because that's not there. And then you got half rho u squared. That is equal to, so at this point, right? So let's just say that this is at h depth. So this will just be P minus rho naught. Oh, okay. What is this once again? The liquid has rho and air has rho naught, right? So it should be rho naught as well. And then, so minus um, rho naught GH. We just call it H, okay? Right. And then you also have this U thing over this, just plus half rho naught U squared. Once again, how are you assuming that this thing is incompressible when in reality it's just a gas and gases are compressible? I have no idea, but whatever, just do it. And this is also equal to, so at this point it's just P minus rho naught GH um, minus, well, yeah, I think that should work. So rho naught G delta H once again, right? Because we're going down once again. Yes. And so the speed over there is just 0, right? Okay, let's cancel some stuff out. So what does that leave us with? It just leaves us with half u squared is equal to negative gh plus half u squared. It's equal to, wait a second, how did this happen? This should not have happened. The flow speed is 0 over there, right? We have, oh, sorry, the pressures are of course different. So wait, but this is the pressure. Oh, it should be plus over here because we're going down, not going up. So it should be plus. Yeah, well, that went wrong, but whatever. Now I know this. So it's just this thing, and then this is equal to what? GH plus G delta H, right? Okay, awesome. Right. So now what? Like, you know what this thing is. Okay, have this equation. Any other equation you know of? Of course, you know another equation, which is that the difference of pressures at these 2 points, which is, well, this is just P naught minus, okay, fine, that, and then this is just, oh, I really just messed up this thing. Oh, wait. The pressure at the, how did I do this? Am I so stupid? I can't just do it like hydrostatics. The pressure over here, it's not P plus rho GH. It's not that. We don't know the, come on, that's just not correct. Yeah. Right, that negative was the datum height stuff, right? Okay, everything went wrong. Everything just went wrong. Not good. It should be like this thing, P1, and it is in fact negative. What am I doing? P2 minus minus. Okay, that looks cool. Right, this is what it should be. Okay. Yeah. And now what? Okay, P1 is equal to, so that just cancels, which just means P1 is equal to rho naught GH plus P. It's one equation you have. Also, we know that P2, right? That's just, so, okay, P1, right, plus rho G delta H, that's just equal to P2, right? So you can put that over there. What does that tell us? that, okay, this first of all cancels, right? Okay, and then just put that over. It's like half rho naught u squared is equal to, so instead of P2, just put that, which is like, so P2 minus P1, right? Which is just rho G delta H and minus rho naught G delta H. Yeah, that looks cool. So now you know what u squared is. Okay, fine. So just u squared is equal to 2G delta H times rho minus rho naught, and that thing upon rho naught, right? Yeah, this should be the thing. Um, wait, wait a second. Oh yeah, that's just it, isn't it? Wait, you all you have to do is just write these two equations. You didn't actually have to find this and what. Okay, that was weird, but that somehow worked out. So now you just have u squared. So of course u will just be square root of this thing. Now this u times s, that is our q, right? Yeah. So the answer is just s square root of 2 g delta h, and then just have rho upon rho naught minus 1. Very weird. I didn't think this would be happening. Well, whatever. Next question. 118. And this in fact works for any two fluids, not just for you know, not just for air and whatever this thing is, mercury or something. I don't know. Anyway, 318. A wide vessel with small hole in the bottom is filled with water and kerosene, neglecting the viscosity. Find the velocity of the water flow if the thickness of the water layer is equal to h1 and that of the kerosene layer is equal to h2. Okay, wait. Wide vessel with small hole in the bottom. It's filled with water and kerosene, but then in what order? Okay, just water and kerosene. Fine. Neglecting the viscosity, find the velocity of water flow if the thickness of water layer is equal to. Okay, of course, like kerosene will float up, right? It's lower density. That's so obvious. So it's this and that. Fine. Find the velocity of the. So this is just h1, h2. Water there is just h1. Kerosene layer h2. We'll just say this is rho 2. This is rho 1, right? So what do you want? You want the velocity of water flow. Okay, awesome. And it's a wide vessel with small hole in the bottom. Right, this thing. So you have to use Bernoulli's equation once again, but in a less usable form, which is basically energy conservation equation. I hate this. So first of all, the continuity equation says that whatever speed you have over there, the speed at this surface, it's still just pretty much zero, right? So yeah. So now there's water leaking from here. So let's just say it has a volume flow rate Q, right? So then Q dt is the volume that leaked out. So like rho 1 Q. Okay, whatever. What's the energy that leaked out? Half mv squared, right? So like half. Wait a second. And you know what? Just put dv right there. We don't care about q dt. We just put dv. So half rho 1 dv, that's the mass, times the speed squared with which it's leaking out, right? That's the thing. And like this went down, sure, but the more important thing is that what actually happened is like, so you just took kerosene from this layer and put that in this height, and then you actually took the water that was in this layer and you put that into this thing, right? That's what happened. So really the change in our potential energy, what will that be? It will be this thing, rho 1 gh1, right? Because that, and then that's of dv, of course, right? Because gv went down, so rho 1 dv gh1, and then plus rho 2 dv g h2, because now this went down as well, right? Yeah. So this will in fact be the, what should I say? Uh, yeah, your change in the potential energy. This is equal to the change in kinetic energy. or negative of that or whatever. Yeah, yeah, that looks cool. So this is gives us rho 1 GH1 plus rho 2. Actually, this is the negative change in potential energy, isn't that right? Yeah, whatever. Rho 2 GH2 is equal to half rho 1 U square. So that just means, I just hate all of this. So it's 2G, then you have H1 plus H2. So let's just say density of kerosene with respect to water. So the specific gravity or whatever you want to call it. Yeah, and okay, what's this called? The relative density, right? Yes. Okay. U is just equal to the square root of 2G times H1 plus H2 density of kerosene with respect to water, of course. That's what you want to find, right? The velocity, 318. Yes, the velocity of water flow. Cool. So this is our answer. Next question, 319. A wide cylindrical vessel 50 centimeter in height is filled with water and rests on a table. Okay, this is the table. It's a vessel. Cylindrical height what? Height 50 centimeter. Okay, this is just zero point 0.5 meters. Filled with water and rests on a table. Assuming the viscosity will be negligible, find at what height from the bottom of vessel a small hole should be perforated for the water jet coming out of it to hit the surface of the table at the maximum distance from. Okay, this we have done countless times, have we not? It should be h upon 2. Yeah, because the v thing, right? So the speed with which it will come will be like, so if this thing is h, then it will just be sort of 2 gh, right? um, and the range. Okay, first of all, just I should just say the time period. The time period is just square root of, so like think about it, half at squared equal to s. So t is just equal to square root of 2s upon a, which is sort of 2 times s. It will just be capital H minus small h, which is, so capital H is this, is just this whole thing, and this upon, what was that, g, right? Yeah, because after this leaves, it just free fall. So yeah, well, that makes sense. Okay, so you got v, you got t, multiply them, you'll get the range. So it's just 2 square root of h times h minus h, and you know how to maximize this function. It will happen when h is equal to capital H upon 2. So yeah, so it's just 0.25 meters or 25 centimeters or whatever. Next question, 320. Oh, and you also want to figure out the L max? Oh, come on, seriously. So what was the thing? Two. You also had G actually. Yeah. Wait, no, you don't have G. That got cancelled, right? Just back. Just go back. So yeah, you don't have G. Just got cancelled. Like it's 2 square root of H times H minus H, right? Okay. So this should happen at 25 centimeter, and this will just be 2 square root of 25 times 25, of course, which is 2 times 25 centimeters. So like 50 centimeter is the range. Next question, 320. Uh, a bent tube is lowered into a water stream as shown in figure 1.83. Okay. The velocity of the stream related to the tube is equal to v, which is equal to 2.5 meter per second. Okay. The closed upper end of the tube located at the height 12 centimeter has a small orifice. To what height will the water jet spurt? Okay, okay, I can do this, no big deal. Uh, yeah, right. So this is just V over here, and then, hey, you know what? I think there might be a better way to do this, other than actually figuring out what the pressure over here should be, and then, yeah, let's not do all of that. Some other way, huh? So what were our assumptions when we did that? Oh, our assumptions were that, right, okay, just comes out and then like, okay, fine, it has to go up as well. The pressure is the atmospheric pressure throughout, right? So even though it's looking like it's diverging from that point, we'll think that it's not. So it's not diverging, it's something like a fountain or whatever. So, okay, fountains do diverge. Something like a laminar fountain. Yeah, just that we can apply the Bernoulli's equation, right? Just so we can do that. So then you can just do it directly, I think, right? Because at that point, your V will be 0. You have gained a height of h naught plus h, right? Yeah, that looks cool. So you have gained that height. And what else is the thing? Oh, and over here, your pressure is actually the atmospheric pressure as well. So then just apply Bernoulli's equation at this point and at this point, right? Is it wrong to do that? Or maybe? Um, no, I mean, after it leaves this, so till it leaves, you can apply the Bernoulli's equation in any case, right? And that's how you get Torsley's theorem. So after it leaves, your delta P is just, wait, not delta P. The pressure is actually constant, just atmospheric pressure. So the change in our, yeah, like half rho v square, the change in that's just equal to negative rho g h, right? So that just fits into our Bernoulli's equation in any case. So you might as well just apply Bernoulli's equation at this point, at this surface, and at this topmost point. So over here, what you have is P naught plus velocity 0. Actually, no, it's not 0. It is actually moving, right? Yeah. Okay, half rho v squared plus, just consider that to be our datum, and this is equal to, so over here your pressure is essentially just P naught, your velocity is 0, and your height that you have gained is h plus h. What is this h naught? Okay, so there you go, that's our equation, which means that v is just equal to square root of, oh, what do you want to figure out first of all? So it's 320. Oh yeah, so the h value, right? Okay, so h is just equal to uh, v squared upon 2g minus h naught. Let's calculate that. Let's just put that. Okay, so 320, what were the values? V was 2.5, just 25 upon 4, that times of 2. G will assume to be 10 minus h naught. H naught is 12 centimeters. What? Centimeters, seriously, 0.12. Why do they make this harder for us? So this is 25 upon 80. Okay, which is like 2.5. Okay, whatever. So this would be 3 point, then you got 1, right? So 1 upon 8, I think, yeah, which is just 0.125, I think, yes. 9 upon 10, so it should be 0.3125. That doesn't make any sense. How can that? Okay, no, it does make sense. Okay, 0.3125. It is in fact bigger than this thing, right? For 1 second I thought it was smaller. It's 5, 2, then minus, this is just 9, and then 2 minus 1 is what, 1? Yeah, so 0.1925. I hope that's correct. Next question. 321. The horizontal bottom of a wide vessel with an ideal fluid has a round orifice of radius r1, over which a round cylindrical, okay, figure 1.84, which is this. This is our round orifice, okay, on which what? On which a round closed cylinder is mounted, whose radius is something r2 bigger than r1. The clearance between the cylinder and the bottom of vessel is very small. The fluid density is rho. Find the static pressure of the fluid in the clearance as a function of the distance r from the x of the orifice. And the cylindrical, what? And the cylinder, okay, sorry, and the cylinder. Wait, what about this? Static pressure of fluid in the clearance as a function of the distance r, right, from the axis of this axis of the orifice. Okay, Oh, and okay, fine. The orifice axis is the same thing as the cylinder's axis. If the height of the fluid is equal to h, okay, this is happening, and this right. So this area through which it's seeping, it's very small compared to whatever this thing is, right? Yeah, that's what we are assuming. And what else was given to us? Okay, so let me see what right connection. Very weird actually. Right? Static pressure of the fluid, the clearance, right? Okay. Uh, yeah, just try to do it. So assume radial symmetry, right? So then I'm just gonna take the top view of this thing, although you cannot actually view it from the top, but then just think about it. So you have this um, hole of R1 into which water is going down. We don't care about the hole really. We care about what's around it. So then till at least the radius R2, right? So at some radius R, you have speed U. So radially symmetric, and that's why we're assuming U is radially inside, right? And this is the thing. Okay. Once again, we want the continuity equation to work, right? And so since we want to, okay, you know what? Let's not do the usual thing that we do. Instead, just use the del dot u vector equal to 0 thing, right? So what I was going to do is that think of all of these elements combined, right? So you just have like 2 pi r times u dt uh, times whatever the height is for this thing, right? This would have been our volume element that like went inside or whatever. And this must be just equal to q, right? Yeah. So this is actually kind of a constant. So I should say q dt or whatever, which means that u is inversely proportional to r. Basically, that's what we are getting at. That u is equal to q upon what is this thing? 2 pi r times h, right? Yeah, that's what I was going to do. And you know what? Just actually check whether or not this is going to work using the del dot u is equal to 0 thing. So we already have it in the cylindrical form. So we only need that, like u r upon r plus. We know with respect to theta and z hat, nothing changes in the first place. So skip all of that. It is this thing. This must be equal to 0, right? So u r upon r, that will just be what? Q upon 2 pi r squared h. And then plus partial u r upon partial r, that's just going to be negative. Yeah, you get the thing, right? It just becomes 0. So yeah, that works out. So what that means is you found out u as a function of r. Now we can figure out the static pressure as a function of r. Easy as that. But for that, first of all, we need to know what the pressure is at this point or something. Hey, we also, wait, what kind of fluid are we dealing with though? It's 321. 321. Ideal fluid, right? So just assume no viscosity. Yeah, just do that. Huh, interesting. What about the vorticity though? Do we have to think about that or not? I don't think we have to, because there is really just, yeah, throughout this, there's no vorticity, so you can just apply Bernoulli's equation in any case. And okay, you can apply over there. And okay, so you can use this fact that there's no vorticity in this region to extend it out of this as well, and then just go up, right? So at this point as well, so actually along this whole streamline, there's no vorticity, which means you can apply that the Bernoulli equation at this point and at any point on this, which is basically at this point, right? So at this point on the surface, what do you have? The pressure is just P naught. Then you have plus, so the velocity is 0 at that point, or approximately 0. Then you have rho gh. This is equal to, at this point, we'll just have, uh, once again, what was the thing? Hey, what do you have to figure out, by the way? 21. Static pressure of the fluid in the clear sense of, okay. The fluid density is rho by as a function of the distance r from the axis of the orifice and is cylinder if the height of the fluid is equal to h. Wait, something's weird about this. Sure, you have u as this thing, but you know what? No, first we'll just figure out what u actually is, and then we'll do anything else, right? No, wait, we need the static pressure, not. That's kind of complicated, isn't it? Hey, what's the pressure at? So, what's the pressure at this point, though? We don't know. But at the very far point, okay, that's just going to be P naught plus rho g, which is okay. That works out. And then at that point, at this point, what is your u vector? It's just something. Unfortunately, it's not zero. Well, that's a problematic thing. Anything else that you know? I wish you could have made this cylinder very big, then everything would have worked somehow. But no, that's not possible. Huh. Because what I was thinking is if you just made it really big, then this thing as r approaches infinity would approach zero in any case, right? So you would be able to write that pressure as, you know, P naught as well. But right now you can't. So you'll have to write everything using Q. And that's not something I want to do. Come on, what can I do? I did the energy equation and that gives me this thing, sure. Something that you can do, come on. Hey, it would be nice to know what actually this, what's the surface area of this open surface, right? That would be really nice to know, don't you think? Because like you will have height decreasing and, okay, no, don't get into that. Not really nice. Okay, no, don't do that. Think about it. You will have u as a function of q everywhere. We don't want that. We don't want to involve q. So what do I do? The clearance between the cylinder and the bottom of the vessel is very small. Oh yeah, of course. And the fluid density is rho, find static pressure of okay. But without q, how am I supposed to write this out? It doesn't make any sense. I mean, this velocity, it could be anything, right? Yeah, it could really be anything. You would never be able to know anything from that. Okay, it's not making sense. Come on, think. It's not like you can apply Tosley's theorem over there. Hey, wait. At this point, at R1, the pressure is at the atmosphere. Look over there. There's a slight opening, right? So inside of this, you just have atmosphere seeping in, which means at R, right? That's our boundary condition that R1 has the pressure P naught. Oh, I should have known. Right. So that's awesome. So you can just figure out what the pressure, sorry, what the U value is at R1, and there you go. You got the thing, right? So you can just write, let's just say U is equal to, you know, R1 upon R times U1, right? And then you can figure out what U1 is, and you are good to go. Okay. So P naught plus rho g h is equal to, so at this point you have pressure P naught. That's the main thing. Equal to P naught plus what our, yeah, this thing. So half rho u1 squared, right? Which means that u1 is just equal to square root of 2gh. Wow, that still worked out. I mean, it's just Torricelli's theorem once again. Yeah, very weird. Why is this Torricelli's theorem once again? I have no idea. Was this is not like this area through which it's seeping. Oh yeah, the area is in fact small, although it's not exactly like a pinhole opening. It still works out somehow. Okay, awesome. So then this is good. U1 is equal to sort of 2gh. Just put that in there and then you get the thing. So U is equal to what? R1 upon R, and then you got square root of 2gh. Awesome. Yeah. So you got U. Now you just need to figure out what the static pressure should be. Yes. Uh, right. So this is equal to what? This thing is just equal to P plus half rho U square in general, right? Yes. Okay. So then P is just equal to what? P naught plus rho GH minus half rho U squared, and then just put U as this thing, and you will get the expression, which is P naught plus rho GH minus like square of this thing, right? Okay, so 2gh is there already. So just gh times this thing, okay, rho gh, and you got r1 upon r squared. Awesome. Isn't that nice? Okay, so that's the static pressure at any point which is at a distance r from the axis. Next question, 322. 322. It is, wait, where's 322? What work should be done in order to squeeze all the water from a horizontally located cylinder? 1.85. 1.85. Okay. So squeeze out all the water during the time t by means of a constant force acting on the piston. The volume of water in the cylinder is equal to V. Okay. The cross-section area of the orifice is equal to S, with S being considerably less than the piston area. Wait. Oh, so it's okay. So you have a time limit. What I was thinking is, okay, if you could do this for in like a more reversible way, you can't do it in the reversible way, of course. You can't suck the water inside. That doesn't make any sense. Um, but if you could do it very slowly, then the speed of the water leaving out would be zero, right? Approximately. Okay, in fact, zero itself. When our time required for doing this approach is infinity, then it would be zero itself. And then you just get the minimum work that you have to do to squeeze out the water. But then no, you are also giving kinetic energy to the water molecules now because you are doing it under the time limit. So right. Okay. Right. By means of a constant force acting on the piston. So the force is constant. Awesome. The volume of water in the cylinder is equal to V. The cross-section area of the orifice is equal to what? S, with S being considerably less than the piston area. The friction and viscosity are negligible, small. Ah, wait a second. Can't you just do F dot S to get the thing done? Because that is the work done by you, isn't it? Huh. The pressure is the same everywhere, and that is the work done by you, of course. So, right. I mean, why would this be so complicated? It's just so why constant force and oh, you don't know what the force is. Right. That explains it. Uh, and you want to do this in a time t. Okay, okay. Now I get what's going on. Fine. So over here you have pressure P. Over here you have pressure P naught when it's leaving out. Here you have speed V. Here you have speed approximately zero. So just P plus nothing in fact because there's no gravity involved. Just P naught plus half rho V squared, right? Okay, so our V is just equal to let's say delta P. So 2 delta P upon rho, the square root of that thing. That's our V, right? Okay. So our Q thing is just equal to, and what is the area of this thing though? Right, okay, that's small s, right? That's area of the orifice. So S square root of 2 delta P upon rho. This thing is Q, right? I guess that works out. Right. What that means is the time required is just delta V upon this thing. No, just V upon, because there's no delta involved. Right, so just V upon S, square root of rho upon 2 delta P. That's the time required. Cool. So then you can figure out the force in this way, because now you have an expression for delta P. So just S T upon V squared is equal to rho upon 2 delta P, which means that delta P is just equal to rho upon 2 S squared T squared, because yeah, it's gonna take forever, right? Okay, and that times of V squared. Okay, delta P is just P minus P naught, so this is just like, yeah, P naught plus this thing, that's equal to P. So just do P times V, and that's going to give you the work done, right? Yeah. So you just get like P naught V. So you are working against the atmosphere, and you are also giving the things like kinetic energy. So yeah. So as T approaches infinity, you see that this term goes to 0. That's what I was talking about. That would be the minimum work done. Anyway, now you got a more general expression in this. Okay, next question. Next you have 323. Okay, right. A cylindrical vessel of height h and base area s is filled with water. An orifice of area s is, so small s, is open in the bottom of the vessel. Okay, neglecting the viscosity of water, determine how soon will the water pour out of the vessel. Didn't we actually already do this thing? Something like that, at least. It doesn't. Okay, no, I don't think we did that. Huh, not good. Anyway, just do it now. So 303, what is the thing? Cylindrical vessel of height h and base area s is filled with water. Right? Let's write down some differential equations. So the base has the orifice, right? Okay. So V will just be equal to square root of 2gh, where h is now a variable quantity, not what it was given to us, which we'll call capital H, whatever. So a Q thing, which is basically like what? Capital S, and then you got negative dh upon dt, that's just equal to small s. Oh, this is gonna get confusing. Let's just say small s upon capital S is equal to, call it x if you want. So this is just equal to this thing. So what do you have? You just have negative dh upon dt is equal to x square root of 2gh. So yeah, that goes inside. Just negative dh upon square root of h is equal to x square root of 2g times delta t. Okay, sorry, dt, right? Dt. Now integrate this thing. So it's negative 1 upon 2 plus that is 1 upon 2. Okay, so 2, negative 2 square root of h, as it goes from h is equal to capital H to 0, right? Because you want this to be emptied. Or you know what, actually just do it the proper way. Just, yeah, capital H to small h, right? That is just equal to what? That's equal to x square root of 2g times the time required, right? So 2 square root of capital H minus square root of small h, that is equal to x square root of 2g times the time required. Okay, or you can just say the time required is equal to square root of 2 upon g, and then you got 1 upon x, and then you got this thing square root of capital H minus square root of small h. Yeah, that looks cool. So that's the time required, right? So the time required will just be what? Who am I getting? I mean, you can always do it by logic. You don't need this thing, right? Just don't need that. Yeah, it will just be this thing. So this is capital S upon small s, right, in the proper way, so that you actually understand what I'm writing. Capital S upon small s, and then we just have this thing. So square root of 2 upon gh. Cool. Next question. 323. 4. A horizontally oriented tube AB of length L rotates with constant angular velocity omega about a stationary vertical axis O dash passing through the end A. Where is it? Okay, figure 1.86. All right. Wait, let's go 324, right? Okay. Uh, the tube is filled with an ideal fluid. The end A of the tube is open. Fine. The closed end B has a very small orifice. Find the velocity of the fluid related to the tube as a function of the column height h. Wait, what? The closed end B has a very small orifice. Velocity of fluid related to the tube is a function of the column height h. What column height? Oh, this is a column height. I thought it's like column length. It's not even a column. It's like whatever this thing is. Yeah, so you just have to figure out the velocity at this point, right? Okay, cool. How bad can this be? Yeah. Uh, so does energy conservation still work? I think it might. Uh-oh. There's a bit of a problem with this thing because, oh no, it's going to be so problematic. There's the pseudo force acting on it all the time. Oh no. Over this. It also has the dr upon dt factor over here. There's the Coriolis force as well, and this just becomes really bad. Uh, so can energy equation, so the energy conservation thing still work? Maybe, maybe not. Come on, think about it. Energy conservation will still work or what? It's like throughout the streamline. Oh, actually, throughout the streamline, your so your velocity is not that big, in fact. So your energy conservation still might work, in fact, because yeah, only at this point do you actually get any acceleration, if at all, and that too, yeah, like the acceleration, it's not impulsive; it's instantaneous, right? So we don't have to. Sorry, it's not impulsive; it's a finite value, so we don't have to worry about it. So we only have to figure out the velocity of this liquid leaving immediately. We don't want to know what happens once it leaves, right? Okay. So then, yeah, just apply Bernoulli's. Sure. Okay, and then of course is omega square r factor coming inside. So that is another complicated thing. First of all, what do you have? This line, it is under the constant atmospheric pressure, right? Or so it would be. Okay. Then after that, okay, it's just air. There's like no density for air, so it doesn't really matter. And then it just, yeah. Since there's no density, you don't need a pressure gradient really. So it's the same pressure over here as well. So it's just, yeah, it's just P naught. And then after that, you need a pressure gradient because, right. So what will you will have is like P naught plus, um, so like rho h, so I should say dh or something. Dx will be better, I don't know. So rho dx times, so basically like mass times volume. So what? Mass times acceleration, but that upon volume, right? Yeah, this is very weird. Why do you have this thing? P naught. Come on, seriously. So just have this, right? You have dp times a, that's this force, that's just equal to what? Omega square r times the mass, right? So the mass is just dv times rho. Now dv is just a times dh. So basically dp is equal to dh times omega square r times rho. So you just want to integrate this thing or well, whatever. We don't need p naught. We just need, okay, fine. Just do it properly. So that's the equation. This is not supposed to be dp. It's supposed to be dh. Sorry. Okay. So dp is or dx or whatever, or dr if you want. So omega square r dr times rho. So the pressure, change in pressure. Change in pressure is just rho omega square, and then r the integration, that is r squared upon 2 going from something to something. Initially, it's just L minus H, and finally, so at this point, right, we just want the pressure at this point, right? It's just going to be equal to L. That looks cool. Then what does this become? Right, so our P minus P naught is equal to rho omega square upon 2 in this stuff. So L square minus this thing, okay, it's just H times 2L minus H. Awesome. So now that we have this thing, wait, what was I going to do? So you have the pressure, sure, and you can apply energy conservation even more, right? And what you will just get is, okay, outside pressure is just, it's just P naught, right? Yeah, yeah, I mean, the outside pressure is in fact P naught. What else would it be? Am I sure about that? Why is this looking weird? Just assume P not equal to yeah, just assume P not equal to 0. Okay, that's not a good assumption, first of all, but they didn't tell us what P naught should be, right? So we can assume it to be 0. Who cares? And I know it's unrealistic because this water will just vaporize, but still, ideal liquid, it doesn't vaporize. Anyway, I think the outside, so the outside force retarding this, that would be P naught times A, of course, right? What else could it be? I don't know. Fine, just put it as P naught. What that means is, uh, yeah, this leaving out will have velocity of square root of 2P minus P naught upon rho, right? Which just becomes square root of omega square h times 2L minus h, right? Yeah, which is like omega square root of h times 2 plus h. This is our V with respect to the tube. Okay, and that's what you want to find, right? Yes, I think so. So 324, the answer is this thing. Oh, okay, they even put that in quotations, height h. That's weird. 325. Demonstrated in the case of steady flow of an ideal fluid, equation 1.7a turns into Bernoulli's equation. What is equation 1.7a? Just keep going. 1.7a. Oh yeah, this thing. You know what? In fact, Bernoulli first derived his equation from this equation, which is weird. Uh, yeah, what was the thing? What did he do? Yeah, he just took a dot product with the velocity vector, right? And then he integrated or something. It's a weird thing happening over there. So you will have to take a derivative. Okay, sorry, you will have to take a dot with v vector, and does that make sense or what? So v dv upon dt, isn't that like, or v vector dot d vector upon dt? It doesn't matter. It's just 1 upon 2 d upon dt of v squared, right? So we just have this thing half rho the time derivative of v squared. So just taking a dot with v vector, right, which is the velocity of the block that is moving, all right? Yeah. So as it moves, how does v square change, right? Okay. This is equal to, so f minus del p. Okay, that dotted with v. So first of all, f dotted with v. What does that tell us? Why does it look so familiar? I have no idea. This should just be v, right? Yeah. Anyway, just f dot v. We don't care about what that actually is. So, whatever. And then you want minus del p, that dotted with v, right? That's going, yeah, that is just becoming weird. Oof. Wait, what would that actually be though? Oh, I think I know what that is. It's just a little weird. Right. So this is the kind of like what we call the material derivative, sorry, the convective derivative, except that it doesn't have that partial p upon partial t term. Otherwise it's just good, right? Yeah. So it's just this thing. You can also write this thing as v vector dot del vector applied on p. Now usually you just have a vector over there, but then you can also have a scalar. What's the big deal, right? Okay. And then we just integrate with respect to time. So we'll have 1 upon 2 rho v square is equal to, now the integration of f vector dot v vector, that's like f vector dot integration of v vector, but then integration of v dt, that's just exactly the definition of displacement, not definition, but yeah, that just becomes the displacement, right? So this is just f vector dot the displacement, which we'll call, let's say d vector, whatever. You know what? Okay, here's a better thing. H vector, right? Yeah. Or let's just say F times H, where H is the H is the just the displacement done along the. Okay, maybe that's not what I should be doing. Okay, yeah, like H is the displacement done opposite to the f vector thing, right? Then you can write this thing as negative f times h. Why am I taking opposite? You will see in a moment. Just negative f h. Then minus, so this thing, right? Now this is kind of weird. You might think it's very weird at the first scene, but trust me, I know what I'm doing. So partial p upon partial t plus v vector dot del vector times p. This is just dp upon dt, which is how the pressure of the element is changing. All right. So this just becomes this thing. It's just minus dp upon dt, but then that times of dt is just dp. So how the pressure of that particular element is changing, not for the point in space. No, for an element that is moving along the streamline. All right. So the integration of this thing, that would just be the delta p thing, right? Yeah. So what does this tell us? It tells us that delta p, in fact, when we integrated this thing, it should really just be delta of v squared. And this should also be just delta h. So the displacement, yeah, call that as delta h. So what does that tell us? Like delta p plus f delta h plus half rho delta v squared is equal to 0. And then you can write it also as f plus, sorry, p plus fh plus. So this h has to be calculated from a reference point, but then whatever, does it really matter? Just choose a reference point, right? Then you got half rho v square is equal to 0, right? Yeah. Oh, sorry, not 0, it's equal to constant. Because delta of that is equal to 0, right? So it's equal to constant. That's exactly the Bernoulli's equation, except that you have to still put f is equal to rho g, and that can be done easily. You can see that, right? So f will just be rho g. In case it's just gravity acting, it will be that thing. And mostly, yes, it will just be gravity acting. So you can just put that in there. It will be rho g. What am I writing? It should be rho g. So that's how you get the Bernoulli's equation. There we go. So yes, I proved that it can be done just like that. So this is done. Then let's go to 326 now. Which is on the opposite sides of a wide vertical vessel filled with water, two identical holes are opened. Vertical vessel filled with water. So here's the vertical vessel. Okay, this is filled with water. On the opposite sides. Okay, so on this side and on this side, whatever. Two identical holes are open, each having the cross-section area s is equal to 0.5 centimeters square. The height difference between them is equal to delta h. Oh, so one of them is like this and the other one is like this. Okay. Find the resultant force of reaction of the water flow coming out of the vessel. Okay, fine. So the force of reaction of the water. I get it. It's just not good. That's the problem. So there's the atmospheric pressure acting on this system that we will consider, right? Our system considers of the water just about to leave. Everything else, yeah, that's our system. So the atmosphere is putting zero force on our system, right? And when water starts to leave, what happens is just conservation of momentum, and that actually gives some kind of acceleration to our remaining system. And m times that is what we call the force, right? And of course, you can do it in a different way, like relative velocity times m dot and whatever. Yeah, so both work, and yeah, just do it the conventional way, right? Relative velocity times m dot. Okay. So once again, what was the thing that? Okay, wait, that's the problematic because you will have pseudo forces in that case. That's just not going good. You want to do energy conservation, right? Mhm. Accelerating fluids. Okay, I know that when a fluid is not accelerating and moving with a constant velocity, we can still use the pressure as we usually do within the reference frame of the fluid, right? But when it is accelerating, it's kind of a weird thing, right? Uh, yeah, force of reaction of the water flowing out. Yeah, okay, so what is the, just say it's moving with acceleration A in that direction, right? So first there's, oh no, this is just very bad. Oh God. Yeah, this is not helping. This is not helping. And this vessel is what? It's open to atmosphere from somewhere or something. Uh, so nothing's given to us. Huh. This is the worst that could happen. They didn't even actually tell us what it's actually happened. Okay, so they don't, yeah, they just didn't tell us whether or not it's open to atmosphere or not. Wide vertical vessel filled with water, 22 volts of each, 5. I get that, but then I need you have square root of the change in pressure, right? You don't have linear thing going on. So how am I going to find out this without knowing what the pressure inside the box is? Should we just assume that this end is open to atmosphere? I don't think that's the correct thing to do. Think about it. What are we going to do? Uh, what do you want, by the way? You just want the resultant force, right? So the thing is like half. Okay, wait a second. Uh, so the force, the propulsion force, will just be m dot times v, right? So right now this guy's velocity is just zero. So that's why I can do this thing. So m dot v, yes, from each side or each hole or whatever. Just want the magnitude first of all. M dot will be just the rho area and then v thing, right? And that also v once again is rho a v squared. So okay, fine. V square is in fact linearly related to pressure, so you can still do it. Fine. So what we'll do is just assume, let's just say the pressure at this point is P. Okay. Yeah. Now you will go up. I'm saying up, but you're just going along the A vector direction. So actually, with in this guy's reference frame, there's a pseudo vector A in this direction, right? Yes. And it's like the inside thing is kind of in equilibrium. It's not exactly, but it is kind of in equilibrium. Okay. So what does that tell us? That means that over here the pressure will just be P naught minus rho AH. Sorry, rho A, whatever this length is. And what kind of vessel is this? It's a wide vertical vessel filled with what? Wait, the height difference. What about this length? It's not given to us, and it also didn't give us any kind of figure, huh? Uh, Wait, without knowing this, how am I going to do it? Also, you can't just put these very close to each other, because if you do that, then yeah, everything gets complicated, doesn't it? Yeah. They didn't give us what this length is, then what you have to do? Assume it's zero, like something like that. I hate to do this, but then I don't have any other choice. So we'll just say, okay, this is not here in the first place. So then, yeah, the change in pressure as you go from here to here is just, so if this is at P, this will be at P plus rho GH, right? Yes. So we don't care about this anymore. Okay. And what happens is the water leaking out from here will just have the velocities for a root of 2 and then just delta P, which is like, so P minus delta, sorry, P minus P naught is what we're calling is delta P. It's delta P plus rho GH upon rho, right? And then over here, you will just have sort of 2 delta P upon rho, right? Okay. Yeah. So that means you just want to take the difference of these guys. So like a row A and identical holes, right? Row A, and that row will in fact cancel in any case. It's just this minus that. Okay, that 2 will come out. So it's 2, then you will have delta P plus rho GH minus, or it's rho G delta H, but whatever, minus delta P. So this cancels, you just get this thing. So this will just be 2 rho G delta H times A. This is our force, right? Yeah. It has units of force. This is volume, that times rho is just mass, that times of G is force. Yes, that's correct. Just calculate the thing, and good thing we actually know the density of water, because if it's just water, it's perfect. Okay. So this is our force, and what's the magnitude? Just 2. What's the density? We know that it's 1 gram per centimeter cube times G, which will say just 10 meter per second square, times delta H. Where is delta H? It's just 51 centimeter, and that is of this thing. So just 51 upon 2 centimeter cube. This will cancel with that. Awesome. Right. There we go. So this is just 2 times 10 power negative 3 kgs times 10 times 51 upon 2 newtons. Yes. This cancels. Let's get this thing, which is like 51 times 10 power negative 2, which is 0.51 newtons. Right? Yeah. That's our force, 0.51 newtons. They really just didn't give us any kind of dimensions. So what we can do is just assume this box to be really, really big in some dimension, which would mean that, or just assume that it's actually fixed to the ground, right? You could do that, can't you? So just assume it's fixed to the ground, and then it's actually easy to see what's happening. Yeah, then no need for pseudo forces or anything. Next question. 327. The side wall of a wide vertical cylindrical vessel of height what? H is equal to 75 centimeters has a narrow vertical slit running all the way down to the bottom of the vessel. Narrow vertical slit running all the way down to the bottom. No figure given to us. Side wall of a wide vertical cylindrical. Oh, it's a cylindrical vessel. Okay. Vertical cylindrical vessel. The side wall of that. Okay. Uh, of height something has a narrow vertical slit. So like this. Okay. Running all the way down to the bottom of the vessel. The length of the slit is L equal to something, and the width B is something. With the slit closed, the vessel is filled with water. Find the resultant force of the reaction of the water flowing out of the vessel immediately after the slit is open. Wow, slit is open. It's not a point anymore, it's a slit. This is just awful. Okay, you want to find the reaction force, huh? And that is immediately after the slit is open. So there's no time given for it to get into steady state anymore. So then how do I think about it? The Yeah, okay, so the thing is you just have this pressure P. So at any point close to this slit, you will have this pressure P, which actually is a variable with H, of course. And over here you have P naught right next to it. So this pressure is what is pushing the water out, right? And yeah, the rate at which it's pushing it, we can figure that out. Just P minus, and there is like a pressure difference over here as well, so it's gonna push it up or something. Yeah, but we don't really matter. Yeah, that doesn't actually matter because we don't want the vertical force anyways. Or do we actually want the vertical force? Yeah, do we want the vertical force though? Because that is there, there's a vertical force pushing the water out as it leaks out. But then the force stops as water goes out. Okay. Oh yeah, okay, that force is not impulsive because the gradient is small. I mean, it's not infinite, that's what I'm saying. But over here, so P minus P naught, this upon dx, that's like infinite, of course. So over here, you have a big pressure difference, right? Yeah, that's what I'm getting at. So what will be the velocity acquired as this happens? I mean, immediately after the slit is opened, right? So just after it is opened, oh God, you don't give it time to get into the steady state anymore. How am I supposed to solve this? Okay, P minus P naught times area, okay, which is like the breadth times dx. So let's say this thing is x. So dx, that's the area, that's the force on this thing. It's like water coming from inside. Okay, this is very weird. Yeah, I don't know. There's no way I can do it directly. So F equal to ma won't help because you're gonna get impulsive forces, right? And once it's out, do you still have force on it or not? It's getting complicated. I know what they want us to do. They just want us to do like use Torricelli's theorem for each point. I don't want to do that. Fine, we just have to do it their way, right? Although you can only use Torricelli's theorem for kind of steady state flow, right? Otherwise, it's not good to do that. Then what other choice do you even have, right? So let's do it. So then it changes with H, right? So you have a vertical slit. What are the positions of this vertical slit? Length of slit is given, height is given, all the way down to the bottom, right? Okay, so like this. Okay, cool. So it starts off from here, right? It starts off from x is equal to uh, 25 centimeters. Yes. And it goes all the way till x is equal to 75, or just say h is equal to, yeah, h is equal to 75 centimeters. And then there's water leaking out from that. Okay, cool. Want to find the force? Of course, you can use the formula we got the last time, which is what was the thing once again? Rho. What was the thing? Rho s v square or what? Just m dot times v, which is rho or dv thing. Okay, dv upon dt actually. So rho s v squared, yes. But here s is actually differential as well. So okay, rho v squared. So our force, or this is df in fact. Df is equal to rho v squared times the area, which is just b dx, right? Yeah. So that was cool. And this is equal to what? Just say this is actually H1, this is H2, right? Yeah. So what's your V squared? Your V is the square root of 2gh, sorry, yeah, like sort of 2gh, right? So V squared will just be 2gh. So just have 2 rho g b, and then it should actually be dh, right? Which is h dh. That looks correct. So then just have f is equal to rho gb, then h square the del of that. So yeah, h2 squared minus h1 squared. That looks correct. Okay, awesome. That's the force that it will get. Right, just calculate this thing. So the density is just 1 gram per centimeter cube. G is just 10 meter per second square. Our B thing is what, 1 millimeter, right? Which is just 10 power negative 1 centimeter. Then H2 square minus H1 square. It's just 75 square minus 25 square, right? Which is like 625 times, what is this? 9 minus 1, 8. Okay, this thing or something. Or you can always do just 75 minus 25, just 50. 50 times 100, which is just, yeah, 50 times 100 is 5 times 10 power 3. Okay, then you just have centimeter square. So this cancels with that. Just get this thing. So this cancels as well. And then 5, 10 power 3 g is just kg. So 5 newtons. Yeah, that's the force. Next question, 328. I don't like how they did this. Okay, I mean how I did this actually. So I don't want to use Bernoulli's theorem on something like this because I'm not sure if it actually works on that or not. Whatever. Next question. 328. Water flows out. The main problem is that this is released. I mean, this is just released. That's the problem. If it was released like after, yeah, and then we were told after some time you want to figure out the force on it or something like that, maybe we would have done it without a doubt. But then when it's just released, it doesn't make sense, does it? Whatever. 328. Water flows out of a big tank uh, along a tube bent at right angles. The inside radius of the tube. Okay, where is it? 1.87. Okay, a big tank. Water's flowing out. It's a tube bent at right angles. Inside radius of the cube is equal to 0.5 centimeters. The length of the horizontal section of cube is equal to 22 centimeters. The water flow rate is this, is milliliters per second. Find the moment of reaction forces of water flowing acting on tube's wall relative to the point, relative to the point O. So relative to this point, right? Okay, just that force, propulsion force acting in this direction in terms of this radius, right? Yeah, no big deal. It's just this thing, L rho area V squared. And then now you know what V squared is. It's just 2gh, right? So 2 L rho A G H. Yeah, that's the thing. So just put in these values and get the torque. What is this 388? So L is 50 centimeters. Okay, 2 times 22 centimeters. Then rho is just 1 gram per centimeter cubed. The times of G and H. Well, G will do at the last. What's A? So along, okay, its radius is given, fine. So pi r squared, right? So it's pi 1 upon 2 centimeters squared, fine. Pi upon 4 centimeters squared. And what else? H. H is, they didn't give us H. Oh. Uh-oh. So they didn't want this in terms of H, huh? They want in terms of Q. Fine, you can do that. So what was the thing once again? M dot times V, right? That's the force, which now just becomes rho times Q, and then V will just be Q upon the area. So it just becomes rho Q squared upon pi r squared, right? That is the force. That was actually not that hard. And this times L, there you go. That's our torque. So it's not this thing, it's instead this thing. Just calculate this thing. So just 1 gram per centimeter cubed. Q squared, it's 1 upon 4 liters. What? Okay. A liter is in centimeters cube, right? Because, yeah, centimeter. So it's just 10 power 3 centimeter cubed. Oh, and you want square of it. It's 10 power 6. Okay, you know what? We'll break it. We'll break it into ways. So first is 1 liter cube, which is 10 power 3 centimeter cubed. And then the other liter, which is 10 power negative 3 meter cubed. So that I can get rid of some stuff. Okay, this gets cancelled. This gets cancelled by itself. So just, yeah, 1 upon 4 times 10, nothing. Just no 10 power. It's just meter cubed. And then you also have gram. So gram per meter cubed. That's what? Rho q squared. Not meter, okay, not per meter. It's like grams times meter cubed. And that's what the length into centimeters, which is 0.22 upon pi r squared. So pi, and then what is r? 0.5 centimeters. Okay. Seriously, can't believe this. This is a centimeter square, isn't it? Okay. It's just 1 upon 2 squared is just 1 upon 4 times 10 power negative 2 squared, which is 10 power negative 4. So just become this thing. Goes on top, it becomes what, 100. This cancels. Just 100, and then okay, you can write it like 2.2 upon pi kg meter cube, or am I missing something? Yeah, I think I am. Per second, that's what I'm missing. Per second square, and then also some meters over there. So yeah, it will just work out itself. No big deal. Just Newton meters or joules. Joules is not good for torque. It's Newton meters, right? And yeah, that's our answer. 2.2.5. Approximately how much? 22.10 times 7 over 22. What am I writing? So zero point 0.7 Newton meters, right? Or I hope it is. Next question. 329. A side wall of wide open tank is provided with the narrow in tube. Okay, 1.88. Fine. Through which water flows out. The cross-sectional area of the tube decreases from s equal to something to s equal to something. The water level in the tank is h equal to 4.6 meters higher than in the tube. Neglecting the viscosity of the water, find the horizontal component of the force tending to pull the tube out of the tank. Oh, okay, fine. So it's gonna pull it out. Fine, no big deal. Oh, okay. I think I've seen this somewhere. So, force tending to pull the tube out of the tank, right? Okay. Of course, you can do the propulsion force, right? So because like water is leaving, you will have a force in that direction, and because water is acting, you have a force in this direction. Whatever, right? Yeah. Uh, just figure out the net force on this, of course. Wait, think about it. That's leaving, or that's like force in this direction, that's force in that direction, right? Okay, you can figure that out, no big deal. And what else do you want? So you also want the force to atmospheric pressure, right? Yeah. So there's atmospheric pressure like working throughout it. And okay, so the way to do that is just to flat out this whole thing. So just take the area in the take the component of the area vector along which you want the force, which is of course only in this direction because there's no force in any other direction. Radial symmetry, right? Okay, awesome. So this is which question? 329, right? Okay, what are we given? We are given capital S, small s, and what else? The water level in the tank is h. Okay, cool. So they gave us h and everything. Okay, fine. Just do it. So by the continuity equation, whatever like v you have over here, okay, you will have something proportionally over there as well. Anyway, you know what? Let's actually do everything using Q first. Yeah, I guess that's how we should be doing it, using Q, right? Oh, and by the way, the pressure over here, it might not be the atmospheric pressure. Over here, it is the atmospheric pressure, right? Anyway, just do it first of all. So what do we do now? Yeah, what was I doing? Sorry. Uh, right. So over here, the force will just be m dot times the v thing, but m dot is just a rho q, and v is just q upon a, so it's just q squared upon s. That's the force in that direction, and then similarly we'll have the force in that direction, but that will be like negative. So negative rho q square upon small s. This is actually capital S, right? Yeah. So because of there's a force in that direction. Cool. Of course, this thing is smaller than that. Wait, what? That's weird. Why is this thing smaller than that? Should that be the thing? I don't think that's right. Wait, what? Wait, no, something's not right about this. You want, okay, to pull out the tube, right? So for that, I just want the pressure over here, and then, yeah, okay, you want that. That's pretty much more harder. So some other way. What is this thing? So, okay, and then of course minus the atmospheric pressure times S, right? This is the net force on what, like this system, right? Which contains this thing, right? As well as the water inside. The water, the momentum of the water is actually not changing, right? Yes, that's constant, which means it's just the force, and also there's the other force which we have to calculate, like the force because of this thing, right? This steel part pulling it in that direction. So yeah, the interesting thing is, why is this q square upon capital S? Something went wrong, didn't it? Yeah, because this is actually not pulling it out of the cube, but instead pushing it inside. No, that can't be the thing. That can't be the thing, right? No, for sure, that's not the thing. Wait, this is higher over there. Sure. Something not make sense now. Come on, think about it. It really looks like it's compressive though, because that's what this force is actually telling us. But we know the pressure is higher over there. Wait, uh, wait, the pressure over here. Don't we have to consider that as well? So this pressure, isn't that also acting? Maybe it is, in fact. There's that pressure because of atmosphere. Okay, I understand that. And there's also this pressure, right? Ah, it's getting complicated. So the real forces that we have to take and the non-real forces, like, God, this is so not good. See, that's why I don't like to take our system to be something that contains yeah, like that actually contains matter that's gonna leave the system, right? I don't like systems like this where your matter is leaving and entering. I don't like that. There must be some other way, right? So yeah, some other way, sure. One think about it. The propulsion forces, though, mm, those are just the way those are. You can't change that. Uh, of course, you can always do it like this thing. So you got this frustum, and so you take the water inside it right at this moment. and the first term itself to your system. Okay, we got this force acting on it because of this steel attached to it. Okay, then it's moving. So this water is moving like this, right? Okay, and a part of it is actually doing this thing. Sure. Yeah. So wait, as it leaves out, uh, oh God. Yeah, I mean, okay, that is also a part of this body now. Okay, so there's the force because of atmosphere, yes, and now this is also part of the body. So there is actually no force because of this thing, isn't that right? Yeah, because like this already was at V. Wait, no, no, it's not right. Oh, you gained moment. Okay, that's what we should have said. You gained this amount of momentum, and then you lost this amount of right. That's the way it should be. Okay. So the things that we calculated, right? So Q's like, okay, rho Q squared upon S, that's actually the small s. This is the amount of momentum you actually gained, right? Then minus rho Q squared upon capital S, that's the amount of momentum you lost, okay? Minus P times S, that's the, okay, that's not something. The actual forces that will act on this thing, that's equal to, so you have this force, right, which is in this direction, so we don't take that, it's actually negative of that, right? And there's the atmospheric pressure, right? So negative P naught S. That makes sense? Okay, fine. And then our F that we're looking for, this F thing is the force that will be our answer. So F is just equal to what? Oh, it's still the same thing. Huh, that was weird. Somehow it's still the same thing. Uh, how did this happen? What is this? Seriously, something went wrong, didn't it? So F should be in that direction, and P naught S is also in that direction, sure. Any other force I'm not taking into account? Of course, I'm not taking into account this thing. There's also force because of the pressure acting on this. Okay, I should have took that into account as well. Yeah, that explains everything. Hey, that was the same problem that I got in the rocket equation that we did. Yeah, right. This is just the rocket equation in disguise, isn't it? Except it's not moving. So, yeah. So this should be this thing plus. So this pressure at that point, and that times the capital S thing. This should be also capital S. In fact, yes. Yeah, that's our equation. So just have F is equal to um, P minus P naught times capital S, right? And then you will just have plus, that goes over there, right? So, okay, plus rho Q squared times 1 upon capital S minus 1 upon small s. Yeah, that is the thing. Awesome. So then just calculate this. Oh, first of all, we need what P should be, right? Yeah, just use Bernoulli's on this and that, and you will get the thing. So Q is the same, right? Mm-hmm. Right. You just energy conservation, right? So look over here and over here, right? Okay, I can do this. I can do this. P minus P naught times the Q. That's the rate at which energy is being put into this thing. And that's equal to, so what's the rate at which you are having your energy increased or something like that, right? Yeah. So this is like this becoming that. Isn't that right? So Q dt should be the actual volume, but then that upon dt is going to be that in any case. That is the rho. That's the mass that you will have, and then delta V squared stuff. So just have this thing. U at this point squared. You will have U at the, okay, it should be half that actually. But then remember what U actually would be, it would just be Q upon small s. So Q squared upon small s squared. And then similarly over here, you just have minus Q squared upon capital S squared. Yeah, that's the thing. So P minus P naught, it will just be rho q squared upon 2 times 1 upon small s squared minus 1 upon capital S squared. Then you will have minus rho q squared 1 upon capital S minus 1 upon small s. That looks cool. Yeah. So finally we have an expression for this thing. Hey, shouldn't this be, oh, this times s of course. So this times s, capital S, right? Yeah, that's how it should be. So first of all, we can just take some stuff out. This rho q squared times 1 upon small s. Okay, it should be the opposite actually. Okay, 1 upon small s minus 1 upon capital S. And then inside we'll just have what? In fact, I can take that 2 out as well. So we just have 1 upon small s plus 1 upon capital S times capital S, which is capital S upon small s plus 1 and the minus of 2 basically. Just this thing minus 1. So taking capital S out of this once again, just get like square of that. So just rho q squared upon 2 capital S squared, and then you got 1 upon small s minus 1 upon capital S squared, right? So really it should just be rho s squared upon 2 and then that comes to, okay, you don't want to be doing that. No, you don't, right? So now what? You just need to figure out what q is and then you're good to go. Yes. Okay. Yeah. So just have this coming out of it and then that should be leaving and whatever. You just figure out what the velocity over there should be. Just going to be square root of what? Square root of 2gh, right? That's the velocity at that point. So a q thing is really just small s square root of 2gh. Cool. So square that and put that in this thing. So yeah, that should be the thing. This rho upon 2 s power 4. Weird. Yeah. Oh, it should not be s square, it should just be s because when we take that s out, okay, just take the dimensions, you know. Yeah, this should be what? This should be a force, right? So rho, then q squared, and then s and okay, all of this stuff. So it's got 1 upon s squared, just 1 upon s. So just rho volume upon time. So q is that thing. Then once again, volume upon time because once again just q, and then 1 upon the area. Was S is area, so yeah, okay. Then volume upon area is just height. Rho V is mass upon time times height upon time. So mass times height upon t squared, or like mass times length upon, so kg meter per second. So yeah, it makes sense. It's just force. Cool. And then just square, then put that in this here. So it should just be this thing s cubed over there. We'll just have 2gh and this thing 1 upon s minus 1 upon capital S squared. So just rho g h s cubed times 1 upon, you know what? Actually, let's do this. So take that inside. It's just capital S upon small s minus 1 squared. That is the force. Yeah. All right. Once again, dimensional check. So this is unitless. S times h is volume. That times of rho is mass. Mass times is just force. Yeah, looks correct, I think. 330. Last question. A cylindrical vessel with water is rotated about its vertical axis with a constant angular velocity omega. Find the shape of the free surface of the water and the water pressure distribution over the bottom of the vessel along its radius provided the pressure at the central point is equal to P naught. The water pressure distribution first of all, and oh, okay, the pressure distribution over the bottom of the vessel. Okay, weird. And you also want the shape of the free surface. Yeah, I've never seen that actually. Anyway, let's try to do this thing. So this is how the surface should be, I think. We'll just say this point is our origin. Okay, and our x-axis is along one of the radius, and then this is our y-axis, right? And you have this. Actually, just put it as r because who cares? Or just put it as h. That also works. But you know what? No, just y and x are good. So this is our x. This thing is our y. So what you have? The pressure as you move from here to here is like integration of what omega square x, and okay, this is the acceleration. You want the pressure, right? So okay, dp is equal to omega square x is just the acceleration, and god, the pressure should be higher over here, so it should be negative dp in that case. No, you want centrifugal force, so centripetal force, right? So it should be actually uh, positive. Yes, the pressure will get higher as you move out. So dp is equal to omega square x times the mass, which is just rho, and oh yeah, it should be actually dp times a, I think. Man, this is not weird. Pressure is changing everything. I mean, yeah, what could go wrong, right? Nothing can go wrong, most likely. Yeah, it should be good. No big deal. Or you could always use that other equation that you have, right? But whatever. So dp times a is equal to omega square x, and then you got the density times the volume, right? So just say dv, which is like what the area on which you are doing this, which is actually just, let's just say dA, and then times of dx. Yeah, okay, this does look good, right? This should really do. So just this thing, and then it should be dA over here as well, but whatever. So you just have dp is equal to omega square x, and then you have rho and then dx. And in equilibrium, this is going to happen. Okay. You can always use that other equation as well, right? So what was the thing? Oh, God, I really have to look up for that equation. Okay, just keep going. Where did that go? Yeah, you can also use this equation. So the F vector, it consists of gravity, right? And okay, this is actually supposed to be d with respect to x. So only changing with respect to x, you will have this thing happening. All right. Okay. Yeah, and this is the thing. So our F vector, we are only considering what's happening in the x direction. So we will only take the centrifugal force. Yes. Okay. Sure. What could go wrong? So wait, centrifugal force. Wait, no, there is no force. What I'm talking, there is no force. And then dv upon dt of this block, it's just the centripetal force, right? That's why rho times the centripetal force, sorry, the centripetal acceleration, right? Okay, so rho, then dv upon dt is just the centripetal acceleration, which is omega square x. That is equal to what? Negative del p. Okay. Oh, and this is actually in the negative r hat direction, so I should put that over there as well. So yeah, and then negative del p. So for that, yeah, so it's just going to be what, like the gradient of p is just partial p upon partial r times r hat plus other stuff in t hat and z hat. We don't care about that because yeah. So what does this actually mean? It just means it's, yeah, negative partial p upon partial r times r hat. That would be our equation, which is also what we got, partial x actually. Yeah. So yeah, I mean x and r are the same thing in this case. It's just partial p upon partial x is equal to rho omega square x. That's what we got over here as well, right? So rho omega square x, that dx thing comes down, just becomes this thing. So partial p upon partial x. Similarly, you can do something for y, right? But we can do that already. So this is y over there. Fine. Okay, first of all, just integrate and get the pressure at this point. So since we have this thing happening, uh, the pressure over here will just be, so what's the pressure over here? Just P naught. Then over here it will be plus integration of this thing, just rho omega square x dx x square upon 2, going from this to that, 0 to x, right? So just x square upon 2. Okay, awesome. Oh, it's just Bernoulli's equation. I should have known. I should have known, of course. Whatever. So yeah, this is the thing. P naught plus rho omega square x square upon 2, whatever. This is just so weird. But this is the thing. So this is the pressure over here. Now minus rho g y, that will be the pressure over here, which is also the atmospheric pressure because it's open to the atmosphere. So what that means is omega square x square upon 2 is equal to gy. Yeah, just have y as a function of x in that case. Y is just omega squared upon 2g times x squared. There you go. So the shape is just this thing. Y is equal to omega square upon 2g times x square. Yeah. And what else do you want, by the way? Oh, you also want the pressure distribution at the bottom, right? So where did that go? 330. And the water pressure distribution over the bottom of the vessel along its radius provided the pressure at the central. You know what? Actually, we'll just use H and R instead of this thing. But right, we'll just substitute at the very end. Okay. Provided the pressure at the central point is equal to P naught. Oh, so then what we figured out is okay. Okay, that's just the expression. It has nothing to do with the atmospheric pressure. This should be PA in that case. So the P atmosphere, right? So anyway, at the bottom, what is the thing? So you go below this datum, the same heights, right? So it's just this pressure minus rho g capital H, and this is like this pressure minus rho g capital H. That's a P naught. And you, yeah, the same kind of increment will be there. So it will just be rho omega square x square upon 2, rho omega square r square upon 2. So P naught plus rho omega square r square upon 2. That is the pressure at the bottom. All right, that's it. I think this is it. I'll see you guys in the next video.